let's code linear regression using gradient descent. In the last video, I did sort of a quick explanation, and if you want a more detailed and thorough derivation of it, I will link my blog post in the description. But let's see. So let's just first go through the notation again. So m will be the number of training examples or the number of points. N will be the number of features, so the number of dimensions that each point is in. And y will be 1 by m, one value for each training example. And x will be an n by m matrix. For each training example, we have n values. And w will be our weight, which is just n by 1. So I just made a quick skeleton code as well. So we're gonna use numpy, and then we have a class. We have an initialization for the class. We're gonna have a function where we compute our predictions, which is y hat, a function for the loss, and a gradient descent where we do the update step, and then a main function which will call these functions over and over for a total number of iterations that we choose. So what we need to first is we're gonna have a learning rate. Let's set it to 0.01, and we're gonna have a total amount of iterations. Let's say we run it for 10,000. And let's see, so y hat, remember that y hat is just w1 x1 plus w2 x2 plus w3 x3 etc x3 etc. So the trick here is that we added x1 as just 1, so just to make the notation more compact. But really, this is how it would look like, right? We would have one intercept value and then the rest. But if we say that we have x1 here, which will be initialized as 1, then we know that we just want the output of this should be one scalar value. And so y will be the same shape as y hat, so 1 by m, and w is n by, so x is n by m, w is n by 1, and we want to have a scalar value for each training example. So the output should be 1 by m. And how we do that is we take w transpose times x, right? Then this transpose would be 1 by n times this, n by m, which will give the output 1 by m. So here we can just return x. Then the loss will be 1 over self.m, which we define later, and times the sum of y hat minus y squared. So np.power y hat minus y comma 2. So we take each, we subtract it, and then we take each element y's squared. And then just the sum over all of those, and also the average. Then we just return L. And let's see here. So this might be the most difficult step, the gradient descent step. In the last video, I think I showed the formula with loops. We're going to do it vectorized. It's still going to be the same thing, just more efficient code. But let's just first think about it in the most simple way. What we want to have returned from gradient descent, like when we compute the dl dw, is a vector of size n by 1, right? Because what we want to do later on is just take w minus w. We can write this first actually, minus the learning rate times dl dw, right? So the learning rate will be element-wise times dldw. And if we're going to do this for the entire vector w, which is n by 1, we also want dldw to be size n by 1. And we know that, well, first of all, we know that we have to take y hat minus y. And this will be 1 by m. So like one trick you could use is just say, okay, we know that the shape of y is 1 by m. And we also know that the shape of x that we need to multiply with will be n by m. And we want the output of this to be n by 1. And then the idea is, okay, well, how can we multiply them to get n by 1? Well, we can see that if we multiply this with this transpose, then we would get n by 1. So this is y hat minus y, right? This is size n 1 by m. So let's take this transpose and let's multiply it with x. And I guess what you could do just to make sure is like print dldw.shape and just check that it's like the correct shape. But this should be fine. And there's one thing that we're just missing. We need to take 2 divided by self.m times np dot, and then this, and return w. Yeah, and we need to have x here, we need to have y hat, we need to have y, and w for the update. Great. So for the main, we need to send in x and y. And the first thing that we're gonna do is, let's see, we need to add 1 in the beginning, and we need to do it for each training example. Yeah. So we need to add, so the input will be n by m, and we're gonna add another dimension, so it will be n plus 1, but it's only like that one that we add are all just going to be 1s for the intercept value. So let's create x1 to be np.1s, and the shape of it will be, we need to add it for all training examples, right? So we're going to make it x of shape of 1 for all the training examples, and then we're just going to change the input x to be, we just add this vector to the first dimension, right? To the so that it becomes n plus 1. And now after that, we just run, we just initialize self.m to be x.shape of 1 again, self.n to be x of shape 0, and w needs to be initialized as so n by 1, self.n comma 1. And then after having done that, we need to run. So what we want to do is we need to first compute, let's compute our prediction. Let's check the loss for that prediction, and then let's just run the update step. So for iteration in range of self.total iterations plus 1, let's compute y hat to be self.y hat of x comma w, right? And the loss will be self.loss of y hat comma y. And then let's see, w will be self.gradient descent of w x y y hat. And also let's just do, if iteration modulus 2000 is 0, then print let's just use f strings. So cost at iteration like this. And in the end, after that it has been trained, right? The updated W values, we return W. Okay, this code hopefully should work now. We want to just do if so we initialize x. Let's say that x is just in let's see in like a 2D graph. So we're going to have 1 and 500. Remember that we're going to add ones to it, right, for the intercept value. So really we're going to have y equals w1 plus w2 x1 or x2, and this is just a straight line in 2D. Then let's say y, the correct is 3 times x plus some noise. Let's just take so that the relationship is 3 times x, but we have some sort of noise in the correct values. And we need to do like regression. We call the class. We initialize the class, and then W will be regression.main of x comma y. And that should be it. Hopefully no errors. Let's see. Damn, like this is the problem with like Sublime Text, is like there's probably not that big of an error, but if you look at this is like super scary. Let's see. Has no attribute y hat. Okay. Yeah, so let's see, y hat should be like this, I guess. Cost is not defined. Yeah, okay. Yeah, so loss. Nice. Now it works. Okay, so we see that in the beginning the cost is pretty high, and then when we run it, we see that it decreases quite quickly. And yeah, what would be like interesting, I did like I've written this code before, and I added another function that plotted it, so see that it actually like does what it's supposed to. You're gonna have to trust me on this one, or you can check how you code it yourself. But like seeing the cost or the loss go down is like gives a good indication that it's most likely working. Like one thing to be careful with is setting the learning rate. Like if you set it too high, I don't know, I haven't tried it. Let's see, 0.5, it still works. Let's say you set it to 100, yeah, it's going to diverge. But if you set it too low, like if you set it to like 1e minus 100, it's going to take a long time for it to converge. So let's say like 50. Yeah, like for this one we see that it starts decreasing. So if we put it like to this, it's probably going to decrease. Yeah, so this is probably a good choice. All right, thank you so much for watching. Hopefully this video helped you understand how to implement it. If you have any questions, then leave them in the comment, and I usually respond. See you next time.